Okay. So this is the last lesson of the unit. Next class we'll review, and then we test. And these are the same objectives we looked at every time since the beginning. But now we've got to add geometric as the other. And again, everything we're doing today is just going over these formulas, right? You don't have to remember them because they're given to you. You just have to know how to use them. Lucky you. Right? Okay. So the definition of geometric sequence is a sequence in which the ratio of consecutive terms is constant. Right? Ratio meaning if you divide one term by the term before it, you do that all along the way, you should always get the same number. That's probably not what you notice when you look at it. What you notice is probably that it looks like you keep multiplying by the same number. Same thing, right? That number, whatever it is called the common ratio, lowercase letter r. Clicker. Man, I shouldn't have done that. Hopefully I can edit that out. Okay. So notice if the terms are getting bigger, that means the thing you're multiplying by is bigger than 1, right? If the terms are getting smaller, that means that r is less than 1. It's a fraction less than 1. All right, so let's look at these. Are they geometric? If they are, what's the common ratio? How about the first one? You know, and when the numbers are kind of funny, you probably are going to have to take that ratio, right? 10 over 4. 10 over 4 is 2.5, right? What's 18 over 10? How about 1.8? So all I did is check the first 3 terms, right? And there's not a common ratio between those. So I can stop. This is not geometric, right? I just divided 10 by 4 and 18 by 10. Okay, so this will be not constant, not geometric. How about the next one? You know, what do you notice just looking at it? It looks like they're going down by a factor of 5, right, in every one. So what does that tell you about the value of r? I mean, if it looks like you're dividing to get the smaller number, remember, if the terms are getting smaller, it's a fraction. It's 1/5, right? 125 over 625 is 1/5, right? And it's the same if I do 25 divided by 125 or 5 divided by 25, all the way down the line. So it is constant. That means it is geometric. So try this one. Tell whether it's geometric, and if it is, what's the common ratio? Is it geometric? I mean, it looks like 8 over negative 4 is negative 2. Negative 16 over 8, negative 2, right? I can go all the way down the line. 32 over negative 16, negative 2. Negative 64 over 32, negative 2. So they're constant. So it's geometric. And what does that make the value of r? R equals negative 2. Okay, now just like we did with arithmetic, we have a formula for the nth term of the sequence. It's the first one in the list on the formula sheet. an, the nth term, is the first term, a1, times r to the n minus 1. So notice, if you plug in a1 here, right, n equals 1, then you get a1 times r to the 1 minus 1, which is r to the 0. And anything to the 0 power is 1. So then you just get a1 equals a1, which it should, right? That's why it's got to be n minus 1, not n minus 1. Okay, so write the formula for the nth term for these geometric sequences. Okay, so let's see. My formula requires me to plug in two things, a1 and r. So looking at these here, right, I can see the a1 is there, first term. What is the r? 20 over 4, which is 5. So here we go. an equals 4 times 5 to the n minus 1. Right, how about the second one? First term, obvious. What is the r? Negative 1/2. You know, if you don't like the calculation, you can like move to smaller numbers. Just go down the line, right? Because it's going to be constant anyways. So what's the formula? an equals 152 times negative 1/2 to the n minus 1. Okay, let's see. I think this is a U try. Find the formula for the nth term of that. So what you get was the r. 15 over 3 is 5. Looks like you're multiplying by 5 to get the next term. Okay, so here's our formula. an equals 3, the first term, times 5 to the n minus 1. So remember when we said last time about when we get formulas for the nth term of an arithmetic, it looks linear, right? It looks like it's mx plus b. It'll be like something n plus something, but it's kind of linear. That's how you know that they're talking about something which is arithmetic. When you get a geometric, it looks exponential. If you remember when we did the exponential function, so it's f of x equals a times b to the x, that's kind of what it looks like. That's how you know you're dealing with geometric. I mean, notice that every time you increase n, you're going to get one more factor of 5. So that's why you can keep multiplying times 5. Like if I wanted to know the term after that, then n would get one more, and I'd get one more factor of 5. Boom. That's how it works. Okay. That becomes a little important. All right, try this one, which is you got two terms there. Neither one is the first term, but see if you could use them to figure out first the r and then the first term, so you could write a formula. And hint, there's two possible answers here. So just think, just like we did in the one with arithmetic, we had a very similar problem. We were going from term A7 to A16. We had to add the common difference 9 times to go from A7 to A16. In this case, how many times do we have to multiply by the common ratio to go from A2 to A4? 2 times, right? So that's what you're trying to figure out. If I set it up with an equation, I'd set it up like this. A2 times R squared should be A4, right? I know A2, that's negative 12. And I know A4, that's negative 3. So I solve for the R. R squared equals positive 1/4. And then I take the square root, and what do I get? Plus or minus 1/2. I mean, you could actually do this with R as positive or R as negative. Now, let's say that R is positive 1/2. Okay? If R is positive 1/2 and A2 was negative 12, then what was A1? It had to be negative 24, right? So that when you multiply by by 1/2, you got negative 12. So in this case, the A1 was negative 24. So the formula is AN equals A1 negative 24 times 1/2 to the n minus 1. Okay, or if R is negative 1/2, right, then what was A1? If you multiply by negative 1/2 to get negative 12, then to go backwards, you would multiply by negative 2, right, to go from, so that becomes positive 24. So now we have a slightly different formula. AN equals positive 24 times negative 1/2 to the n minus 1. I mean, you can check it out and see, does it work? If I plug in A2 for this first one here, then I've got 1/2 to the first times negative 24, which is negative 12. And if I plug in 4, I'll get 1/2 to the third, which is 1/8 times negative 24, which is negative 3. If I do the bottom one, now I've got plug in n equals 2. Now I got negative 1/2 to the 1 times 24 is negative 12. So it works either way. Okay, the recursive formula, as we saw in the last little bit of the homework there, right? It's not explicit. I can't plug in n and get a value out. I have to know a term that goes before it. For this one, I need to know the term that's right, the one before it. Again, that's what these subscripts of n and n minus 1 means. If you have, right, A1, comma, A2, comma, dot, 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 AN minus 1, comma, AN, comma, AN plus 1. You know, these are just subscripts that are telling you the relative position of these terms in a sequence. So if you know the term before it, multiply times the common ratio, you get the next term, which is kind of the way you look at it anyways. That's why you don't want to get confused by this formula. And if you get a question that says, find the formula for A sub n, don't use the recursive, right? You need the explicit formula. Don't jump on the recursive for that. So let's see. We'll do a couple of these. So, looking at this here, what is the value of R? R equals 3. Right? It's the number you're multiplying the term before by to get the next term. So that tells me if the first term is 1, what's the next term? 3. What's the next term? 9. What's the next term? 27, 81, 243. There's 6 terms. You know, at least if you could look at it and see, oh, that's what R is. Then you know what to do with it. Okay, how about this one? Again, the only thing I need to know is R. So can you tell me what R is in this problem? Right, if I do 40 over 16, right, that's 5 over 2, which is 2.5. So the nth term is 2.5 times the nth minus 1 term, the term right before it. Now, you got to start somewhere, so you should probably add A1 equals 16. Okay, so now you got the first term, you can make the second and the third and the fourth. Okay. Good. So now we get into the sums. Okay. So if you go down in the formula sheet, right, column is geometric. Look at the capital S's, that means sum. Right? When you see a subscript, which is n, that means you're adding up a certain number of terms, right? A finite number of terms. And here's our formula. What are the things we got to plug into this formula to know the sum? A1 is first term, R is the common ratio, N is the number of terms, right? So we don't need the last term. Now, like arithmetic, you need the last term. Here, we don't need the last term. But the math with this thing sometimes gets kind of complicated when you start actually plugging things in. Good, Michelle? Okay. So what is the sum of the first 16 terms of this series? All right, so let me rewrite my formula. Right, Sn equals A1 times 1 minus R to the n over 1 minus R. Okay, what is A1? Is 4. What is R? So the R should be the ratio of consecutive terms, so that's 3. And how many terms are we adding up? 16 terms, so n equals 16. So that's what needs to be plugged in here, right? We're going to plug in 4 times 1 minus 3 to the 16th divided by 1 minus 3. For that, you're going to want to use a calculator, obviously. And this is not a bad problem in terms of these can get more complicated if a couple things are true, right? If the R happens to be negative, then you've got to worry about minusing a negative here, right? If the R happens to be negative and you're raising to an odd power, then you got to worry about that because a negative number to an odd power is negative, right? Those are things that can make this where, you know, there's plenty of places that it's like easy to make a mistake. Okay, this is the way I like to do this. This is just a little trick. Calculator time. Okay, so I'm going to use the calculator, let the calculator do this whole calculation for me in one step, right? First, I need the calculator to understand what are the values of A1, R, and N, okay? So in the calculator, I'm going to use A, R, and N. They don't have an A1. I'll just use A, right? So this is how you let the calculator understand the value of a variable or a letter, right? If I want A to be 4, then I do 4, and then I hit this STO button on the bottom left. You see a right arrow there? And then I hit the alpha A. Alpha A. So 4 arrow A, enter. Okay, now I'm going to see R is 3. So 3 store alpha, and I think that's on the multiply key. Right? And then I want N is 16. 16 store alpha, and that's on the log key. Right? Now I'm going to enter that formula. If you didn't know it, the calculators now have a fraction format in there, so you don't even have to worry about parentheses. Right? Go to alpha y equals 1, and there's your fraction. Okay. Now, what I should have done is before I get to that, let me multiply by the A. Alpha A times, and now I'll get into my fraction again, 1 minus alpha R raised to the alpha N. Get out of that. The caret key right there. See that button right there? Run it right under clear. That's how you raised any power. So raise it, hit that, and then go alpha N, which is on the log key, and then go 1 minus alpha R. Does that look right? A times 1 minus R to the N divided by 1 minus R. You hit enter. There's your answer. So, what's that? You got it now? STO. Right? So, let's say that I'd done this, right? I got my answer, happy with my answer, and then I get to the next problem, and I've got 3 different values for A1, R, and N. Okay, I store those again, and then I don't need to actually retype that formula. It's already in the calculator. You can always get back to something that's in there by going second, enter, and it'll bring up what you just typed last, right? You know, I mean, so let's say, just to show one thing, let's say I restore A as 5, right? 5 store alpha A. Clear. 5 store alpha A. Right. Now, if I'm going to redo the calculation, when I hit second enter, it brings up the last thing I typed, which was 5 store A. If I do it again, it brings up the thing that I did before, which is that formula. So it would just redo the form just like that. All I have to do is restore the constants, boom, and then run the calculation again. You know, in this problem, the answer was 86,093,440. 43,000? That doesn't seem right. 93,000? Okay, I can fix that. But that can be a handy way to let the calculator do it. And then if there's any issues like a minus and negative, or do I put the negative in before I raise it to the power or any of that, the calculator's going to do it all for you. No mistakes. Okay. Okay, so evaluate. Now this is actually the same series as the last page, but now it's written with a summation. Okay, so the first thing is, if you're given that kind of a problem, how do you know that it's geometric? Right? Well, again, what did I say about what does it look like when it's geometric? If it's arithmetic, it looks like it's linear. If it's geometric, it looks like it's exponential. Okay. It looks like it's exponential. And that looks like it's, it's something being raised to a power. So that's how you know that it's exponential, right? Looks exponential. Okay. Okay. How do you know what the R is when you're looking at that formula? It's not 4. It's whatever is being raised to a power, right? That's why when you increment the index I, you always get one more of that thing to multiply by, right? So the R is what is being raised to power. Right. So in this case, the R is 3. How do you know what the first term is, since you would have to plug that in? Right. How do you know the first term? We did this with arithmetic. It doesn't work any differently. You plug in the lower limit, right? You plug in I equals 1 here. So what is that? 4 times 3 to the 0, which is 4, right? So the A1 is 4. And how do you know how many terms there are? It's not the top number necessarily, right? Depends on what the bottom number is. But if it starts at 1, then the top number would be it. 1 to 16, 16 terms. Now, last class, we showed how you calculator actually has this summation notation in it, right? A summation function. So we need to look at that. Okay, this is something that I couldn't show you last class because it wasn't part of it, but now I can show you. So let's go to the calculator, and let me clear it. Do you remember where is the summation function? You can do alpha window, you'll see it, right? Alpha window, there it is, number 2. You can also go to the math menu and it's near the bottom. Okay, so now let me put this in. I'm just going to use X for an index, okay, because it's easy. X goes from 1 to 16. And now, the parentheses that are there, you can't use those that are like your parentheses in the problem. You got to put your formula all the way inside those parentheses, okay? Don't try to use those like stick the 4 in front of that and then use just a 3 in the middle. That won't work. You need to put your formula all the way inside those. So now I'm going to put 4, and I'll do my own parentheses, 3 raised to the x minus 1. Right, so everything I put is inside that formula, their parentheses. And then when I hit enter, I get the same thing that we got before, luckily. Okay, let's try another. All right. So in 1990, the total box office revenue at U.S. movie theaters was about $5.02 billion. From 1990 through 2003, the total box office revenue increased by about 5.9% per year. Write the formula for AN. Okay, so let's see. AN equals what is going to be A1? 5.02, right? They said the first year was 5.02. Now, if it's increasing by 5.9% a year, what does that make the R? No, but you're close. 1.059, okay? You got to have the 1, or else the terms aren't going to get bigger, right? It's going to be the 1 times 5.02 will give you that 5.02. The 0.059 times 5.02 will increase it, right? So it has to be 1.059. That's how you make something increase year to year by 5.9%. And then we're going to use n minus 1 up here. Will that work? I mean, if I plug in n equals 1, they're saying here that n equals 1 represents 1990. So if I plug in n equals 1 here, right, then I got 1.059 to the 0, which is 1, times 5.02, which is good. Okay, that's the formula that we could use for any particular year. You want to know how much money was made? That was how much. Okay, the next question is, what's the total? From 1990 to 2003, what's the total? Okay, well, let's see. If I want to find the total, I have to have the first term, right, which is 5.02 times 1 minus 1.059. And what is n? How many years are we adding up here? If we start in 1990 and we end in 2003, it's actually 14, because 1990 itself was 1, right? So you got to add 13 to that. So that'll be to 14. And then that all has to be divided by 1 minus 1.059. You know, another way of saying it is we could just write it down, right? A1 is 5.02. R is 1.059. And N equals 14. So I'm going to use those in the calculator. All right, I'm going to go 5.02 store alpha A, enter. R, so 1.059 store alpha R, and N is 14. 14 store alpha N. Now I'm going to go through the second enter until I get to my formula back again. Okay, there's the formula for the sum. Hit enter. 104.8 billion. Right, I didn't have to redo the formula. It was already in there. I just restored A, R, and N. But you got to remember a couple things. Like you want to increase it by a percent, right? You got to have 1 point and then the decimal percent. 5.9 is 0.059. So that is 104 billion. Okay. Now the other day I explained that I described a geometric series that would actually, you could add up an infinite number of terms, right? I said if I walk from this side of the screen to the other side, and I'll call that distance 1, by going halfway to the end with every step, then I'm never going to get to the end. I'm always just going halfway to the end, right? I can do this infinitely. I never get to the end. But I'll get so close that we'll say that the sum is the total end. Now, what is the R in that case? It's 1/2, right? I'm multiplying times 1/2 to get the next step along the way. So there are conditions when you can add up an infinite number of terms. And for a geometric sequence, the condition is that the r has got to be less than 1. It has to be a fraction less than 1. And that's what this is about here. Right? So we have a formula. It works as long as the absolute value of r is less than 1, which means that it could be that the r is negative. It could be that your terms are changing sign, right? But as long as it's, the absolute value is something like, negative 1/2, positive 1/2, negative 3/4, positive 3/4. That's all good, right? Negative 2 is not okay, right? Negative 2 is less than 1, but the absolute value is not less than 1. So it's got to be something in between negative 1 and 1. If that's true, which means the terms are getting smaller as you look at them, then what happens when n approaches infinity? I start adding up an infinite number of terms. What happens to a fraction if you take it times itself infinite number of times? 1/2, 1/4, 1/8, 1/16, 1/32. Right? It keeps getting smaller and smaller and smaller. So eventually, and this is kind of going back to our n behavior notation, as n approaches infinity, that term r to the n, that's going to approach 0. If r is less than 1, that's going to approach 0. Which means in this formula right here, that term just drops out. It's gone. Everything else is still there, but this formula then looks like this. A1 over 1 minus r. Right? And that's the last formula here. And again, they use a subscript of infinity. So you shouldn't have any confusion about which formula you're using. If it's an infinite series, right, then use the one that has an infinity in it. Okay. Okay, so let's see. In this one here, right, my formula says that S infinity is A1 over 1 minus R. Okay, how can I tell what's the A1 when it's given in the summation notation? Plug in the lower limit, right? So what is 5 times 0.8 to the 1 minus 1 power? Is 5, right? So A1 is 5. Okay, what is R? 0.8. Whatever is being raised to the power, that's the R. Right, so that's all you've got to plug into this formula. S infinity equals 5 divided by 1 minus 0.8, which is 5 divided by 0.2, which is 25. Now, you could do the same trick of storing A is 5 and R is 0.8 and let the calculator do the formula for you. That would be fine. Could you use the summation notation, right? Could I go to the calculator here and bring up the alpha window 2? So let's say I wanted to do it like that. So I go X is my variable, my index, and then I'm going to go 1. So the question is, what are you going to put on the top? There's no infinity symbol in the calculator. And a lot of people will say, well, you can't do it. You just can't do it. You can do, okay, you can do something. Put in a number that's pretty big, but not too big. And it should converge to the sum pretty obviously, okay? If you don't want to put in something that's ridiculously big, or the calculator is actually sitting there calculating forever, it'll never stop. I think that in the last class we tried 50, and we got close, right? I put in a 50 like this, and then I put in my 5 times 0.8 raised to the x minus 1. I think that's right. Right, and I got 24.999. Didn't quite get there, right? Let's see if I did 100. So I'm just going to go second enter to bring that up. And I'm going to scroll back over the 50 and make it 100. Okay. I don't think I have to do this, but I will. Okay, now it'll go. Oh, not quite there. You know, if I go 101, yeah, I'll probably get it. But you can see, you can come pretty close to an infinite sum in here. You just don't have an infinity symbol. But you know, put in 100. Do you try it again, Gabe? Did 101 do it? Okay, good. So sometimes you might have to go a little higher. You wouldn't want to put if this was like one of those not multiple choice questions on the SOL. You don't want to put in something that's close. They're looking for an exact answer. So find the sum of that. These are the last 3 slides. Right. The A1 was 1. You could see it. The R was -3/4. Right. Just divide the second term by the first, -3/4. So that's all you got to put into this formula. Remember, there's a minus there, but the R was negative. So you got to make that a plus. 1 plus 3/4 is 7/4. So 1 over 7/4 is 4/7. Remember, you can, if you have issues like minus and negative and things like that, you could always just store in the calculator A is 1, R is -3/4, and then type in that formula, right? And it'll do it. It'll take care of it completely. You won't have any mistakes with, you know, negative signs. Okay, how about, that was supposed to be mine anyways. That's okay. Try that one. What's the answer? Should be 2/3. Okay, if you're not getting these right, there's not that much calculating to do, then again, use the calculator in a smarter way, right? If the R is -1/2, then 1 minus R is 1 plus 1/2. So you get 3/2. 1 over 3/2, 2/3. What are you saying? What's that? There is none. There's no infinity. Were you paying attention when we went over that? We said put in a high number, not too high, like 50 or 100 or something like that. Okay? How about that one? Nate? No solution, no sum. R is greater than 1. If the R is greater than 1, you stop and just say no solution, right? Sometimes you get problems like that. If it's in a summation notation, that's what it'll look like, right? Whatever's being raised to the power is bigger than 1. If it's written out in a series, you see the terms are getting bigger. So you just stop, say there's no sum. Okay, last one. The R is 1/4, right? And the first term is right there. So it's pretty straightforward. You just plug in 3/3/4, which is 3 times 4/3, which is 4. The answer is 4. So there's homework.